Imagine looking up at a night sky bursting with stars, each a tiny beacon set against the vast black canvas of space. In centuries past, people believed our own sun, accompanied by its retinue of planets, might be a rare configuration, perhaps even the only one. But the era of exoplanet discovery, flourishing across the last few decades, has rewritten that assumption entirely. Our galaxy teems with stars, many of them harboring worlds of all shapes and sizes. Super-Earths larger than our planet, but smaller than Neptune. Hot Jupiters skimming perilously close to their scorching stars. Rocky planets locked in tidal embraces, and so much more. Even with such a bounty of extraordinary findings, the TRAPPIST-1 system stands out as a dazzling treasure trove. In a single faint red star, astronomers have discovered 7 rocky planets, each roughly Earth-sized, 3 of which reside in that most coveted region known as the habitable zone. This configuration has captured the imagination of scientists and dreamers alike, tempting us with the possibility that at least one of those 7 siblings might harbor the conditions needed for liquid water, or perhaps even life. The first whisper of this system's existence came from a modest Belgian-operated robotic telescope, the TRAPPIST facility in Chile. Designed initially for comet surveys and exoplanet transits, this unassuming instrument turned its gaze on a dim star in the constellation Aquarius, about 40 light-years from Earth. What it found there, starting around 2015 and confirmed in 2016, took the astronomical community by storm. At first, astronomers noted evidence for 3 planets passing in front of that star, periodically blocking a fraction of its feeble light. These signals, known as transits, are a gold standard for exoplanet detection. If a planet is aligned just so, each time it crosses the star's face, it creates a tiny, regular dip in brightness. Further study with the Spitzer Space Telescope, supplemented by ground-based observations, soon revealed that the star actually hosts 7 transiting planets. Overnight, TRAPPIST-1 became a sensation, a living testament to the improbable diversity of planetary systems that can arise around even the smallest, dimmest suns. The star at the center of this cosmic story is but a fraction of the sun's mass and brightness. A red dwarf on the cusp of not being a star at all, barely massive enough to sustain the nuclear fusion of hydrogen. Astronomers refer to it as an ultra-cool dwarf with a surface temperature of roughly 2,500 Kelvin, far below our sun's nearly 5,800 Kelvin. In terms of mass, TRAPPIST-1 weighs in at only about 9% that of the sun. You could stack more than 10 of these tiny stars to match the sun's radius. Its luminosity is so faint that, from Earth, it cannot be seen with the naked eye. And yet, in that quiet corner of space, it has managed to forge a family of 7 planets that somehow ended up aligning their orbital planes perfectly from our perspective, letting us witness each transit as it happens. That improbable geometry offers a rare chance to measure these worlds in detail. Each dip in brightness gives clues to a planet's size, and subtle variations in transit timings caused by the gravitational pushes and pulls of other planets reveal their masses. Wrapped around this cool star, the 7 siblings revolve at breakneck speeds compared to our familiar Earth year. One of them completes a lap in about a day and a half, another in just over 2 days, and the outermost in less than 3 Earth weeks. So tightly are they packed that the entire system could fit well within the orbit of Mercury in our solar system. A star so dim might seem to offer little in the way of illumination, yet because the planets are nestled so close, some of them receive levels of stellar flux that could, under the right conditions, sustain liquid water on their surfaces. The trio that has generated the most excitement sits in or near the so-called habitable zone, where stellar irradiation is neither too fierce nor too feeble. If their atmospheres are suitably dense, And if they possess protective magnetic fields to guard against stellar flares, they might see water pooling on their surfaces or swirling in their air as clouds, one of the cornerstones for life as we know it. From the earliest telescopes that homed in on TRAPPIST-1, scientists have been racing to understand not just how many planets are present, but what these worlds might actually be like. One immediate clue comes from measuring the planet's radii and masses, which in turn yield densities, crucial for distinguishing a rocky Earth-like composition from a gas-dominated one. Thanks to painstaking analyses of transit timing variations, we know these planets likely lack the sort of thick hydrogen-helium envelopes that define Neptune-like bodies. Instead, many appear to be truly terrestrial, with densities pointing to iron cores and silicate mantles. Some are even suspected of harboring substantial amounts of water. Their compact arrangement and near-resonant orbits also hint at a nuanced formation scenario. It's plausible that they coalesced farther out in the star's proto-planetary disk, rich in ices, then migrated inward as the system evolved. The question that has seized public imagination is habitability. On Earth, life thrives thanks to a delicate interplay of atmosphere, temperature, liquid water, magnetic fields, and geologic activity. If the TRAPPIST-1 worlds host the right combination of these elements, they could, in the theory, support microbial life, or at the very least, Earth-like climates. But an ultra-cool dwarf star, for all its gentle brightness, can be temperamental in other ways. M-dwarf stars are known to produce flares, bursts of charged particles and radiation that can wear away a planet's atmosphere over time if there is no robust magnetic field to deflect that onslaught. The closeness of the TRAPPIST-1 planets amplifies that risk. Tidal locking, another likely side effect of orbiting so close, means that one hemisphere may constantly face the star while the opposite side remains in perpetual darkness. Without effective circulation of heat through an atmosphere, the day side might be scorching, the night side sub-zero. Yet climate models do suggest that a sufficiently thick and well-balanced atmosphere could transport warmth around the planet, allowing stable conditions at the terminator region or even across the entire surface, if cloud formation reflects just enough of the incoming radiation. Astronomers have been eager to uncover whether these scenarios hold any truth. Observations with the Hubble Space Telescope offered early hints by analyzing the starlight that filters through the outer edges of each planet's atmosphere during transit. If any planet were encased in a huge blanket of hydrogen gas, it would reveal itself in the spectrum. But that does not appear to be the case here, at least not for the innermost worlds. More definitive answers are now being sought by the James Webb Space Telescope, which has the precision in the infrared needed to detect molecules such as carbon dioxide, methane, oxygen, and water vapor. By measuring subtle dips in brightness at specific wavelengths, scientists can glean a planet's chemical fingerprints. Even the detection of clouds or a global ocean might lie within reach given enough observational time and a bit of luck. It is a difficult enterprise requiring extremely careful calibration of instruments, but the prize is tantalizing, a genuine reading of the atmospheres enveloping these Earth-sized worlds. History shows how swiftly TRAPPIST-1 evolved from a faint, overlooked star to a prime subject of investigation. In the mid-2010s, ground-based transit surveys discovered a handful of planetary signals around it. Follow-up with NASA's Spitzer Space Telescope, designed to examine cosmic infrared light, opened up a more extended, uninterrupted view, revealing the presence of 7 planets. Then came the wave of Hubble and ground-based spectrographic follow-ups, refining parameters bit by bit. Across the globe, telescopes collaborated to measure minute changes in transit curves. Each fleeting dip offered another puzzle piece for planetary astronomers to place in the mosaic. And now that James Webb is operational, TRAPPIST-1 sits high on the priority list of cosmic targets, representing a laboratory for everything we hope to learn about planetary formation, migration, and habitability. The synergy of data from multiple observatories, covering a wide spectrum of wavelengths, continues to sharpen our picture of these planets. Perhaps in time, we will examine the day-night temperature distributions, watch for signs of powerful star flares, or even detect chemicals linked to biological processes. Beyond telescopes already in space, plans for future behemoths on the ground loom on the horizon. The upcoming generation of extremely large telescopes, sporting mirrors up to 30 or even 40 meters across, will push the frontiers of spectroscopy to new levels of sensitivity. Their advanced adaptive optics systems could, in principle, separate the star's light from that of individual planets more precisely, or at least help refine transit and radial velocity data in ways that reveal narrower constraints on mass and atmospheric composition. Concept missions like star shades or space-based interferometers have also been floated as ways to directly image exoplanets in the future. Still a daunting challenge, but one that the TRAPPIST-1 system, with its tight orbits and multiple transits, might help refine. Even so, beaming an actual probe across 40 light-years remains a far-flung prospect that would demand breakthroughs in propulsion technology well beyond our present capabilities. Still, the curiosity remains. If one of these worlds showed strong evidence for water clouds or interesting ratios of gases, would that spur renewed efforts toward interstellar exploration? The structural arrangement of TRAPPIST-1 itself is a marvel. Each planet's orbital period resonates with its neighbor, a mesmerizing celestial dance that prevents chaotic collisions and at the same time gives scientists a chance to measure mass more accurately. The system is so compact that a traveler standing on one planet might see one of the other planets looming in the sky as a disk rather than just a point of light. Gravitational tugs induce minor shifts in transit times, which in turn help pin down the masses and densities. To the human imagination, it conjures a vision of 7 sister worlds locked in an intricate cosmic ballet. The stars' dim red glow casting a muted light across their surfaces. But that faint star, while gentler in visible brightness compared to the sun, emits significant radiation in other wavelengths that could shape or strip planetary atmospheres. Each planet, therefore, faces a tight balancing act between receiving enough flux to warm its surface and withstanding the extremes of stellar activity. Some of these rocky siblings may well be ocean worlds. Others might be mostly barren, with limited amounts of water or none at all. Because tidal locking is likely, that distribution of water could manifest in surprising ways, perhaps forming vast ice caps on the perpetually cold night sides, or swirling as thick cloud belts on the day sides. Internal heating could play a role too. Tidal forces might generate volcanic activity or maintain subsurface oceans, akin to what we see on some of the moons of Jupiter and Saturn. But unraveling these details demands data we do not yet have. More advanced spectroscopic analyses, tighter mass measurements, or a stroke of luck in capturing key atmospheric signals. No matter the outcome, TRAPPIST-1 marks a milestone in our broader search for life. By studying these 7 worlds, we learn about the boundaries of habitability around small stars, which are by far the most common type of star in our galaxy. If it turns out that the environment of an ultra-cool dwarf is too volatile or punishing for life to take hold, that in itself is a profound insight. But if at least one of the TRAPPIST-1 planets manages to retain a stable climate, a protective atmosphere, and hospitable surface temperatures, that raises the odds that countless other red dwarfs could likewise harbor life-friendly outposts. Even in the event that none of these planets is perfect for Earth-like biology, we still capture a deeper understanding of how planetary systems form and evolve under conditions drastically different from our sun's. One of the most dramatic appeals of the system lies in the potential discovery of atmospheric signatures commonly linked to life. On Earth, oxygen coexists with methane in a delicate balance thanks to biological replenishment. If we ever detected a similar imbalance on one of these exoplanets with no clear abiotic explanation, it would rank among the most momentous findings in human history. Confirming the presence of actual organisms would be far more difficult, but an initial sniff of interesting atmospheric chemistry would spark an unstoppable wave of investigation. TRAPPIST-1 is at the forefront of this quest, precisely because its planets are accessible to transit-based spectroscopy in a way that many other exoplanets are not. The star's small size amplifies the transit signal, enhancing our capacity to detect and interpret subtle clues. Look back at the name itself, TRAPPIST-1. It refers to the telescope that made the initial discovery, named in homage to Belgian Trappist beers. The star's official designation is less romantic, but the lore that has grown around it proves how scientific endeavors can intertwine with cultural echoes. Suddenly, a tiny star that once languished in obscurity has gained worldwide fame. Educational programs, documentaries, and planetarium shows highlight those 7 Earth-sized worlds, describing them as an emblem of cosmic wonder. If a small star not much bigger than Jupiter can manage to nurture an entire suite of rocky planets, who can say how many more like it dot the galaxy, waiting for us to notice the faint dips in their luminosity as new worlds transit before our instruments? The story of TRAPPIST-1 is still unfolding. Observational campaigns continue. Each new method, each new generation of telescopes refines planetary parameters or unearths subtle atmospheric signals. At times, flares from the star complicate data sets, adding further layers of intrigue. The star's overall quietness or activity level remains an open question, with critical implications for the survival of planetary atmospheres. As scientific teams coordinate across continents, pooling data from multiple observatories, our picture of TRAPPIST-1 becomes sharper, though it remains far from complete. The next decades promise to deepen the narrative. With the James Webb Space Telescope operational, we have an unprecedented chance to probe for water vapor or greenhouse gases, to measure temperature gradients between day and night sides, or to detect clouds swirling above alien oceans. And should one of the extremely large telescopes on Earth manage, through exquisite adaptive optics, to tease out signals from an individual planet, we might inch even closer to a panoramic view of this cosmic family. In the long run, TRAPPIST-1 challenges us to contemplate our own cosmic lineage. Earth, after all, formed in a different environment, around a star that is more massive and luminous by orders of magnitude. By comparing these two scenarios, the intense, close-in orbits of TRAPPIST-1's worlds versus the spread-out configuration of our solar system, we glean more general lessons about how star systems come to be. It is not so long ago that people doubted whether rocky planets outside our own system were common. Now we know that nature is prodigiously creative, spinning entire solar systems around stars large and small, forging rocky orbs that revolve every few days, some locked in intricate resonances, others battered by intense stellar winds. A sense of wonder permeates every glimpse we get of TRAPPIST-1. If even one of those 7 planets endures in a temperate, watery state, it might host conditions conducive to biology. And even if not, the mere fact that such a system exists suggests that small stars can orchestrate the birth of multiple Earth-like planets, a reality that was scarcely imagined before the exoplanet boom. The resonance chain, the varied densities, the synergy of data from countless instruments, these facets of TRAPPIST-1 speak to the collaborative spirit of modern astronomy. Researchers around the globe share observations, refine orbital models, and dream of the day we might unambiguously detect a life-sustaining atmosphere somewhere among the red dwarfs of our galaxy. In the end, TRAPPIST-1 stands as a landmark. It has expanded our concept of where habitable environments might be found. It has offered a near-perfect testing ground for advanced spectroscopic methods, and it has piqued the public's curiosity about what it means for a planet to be another Earth. The entire saga highlights both the triumphs and the challenges of exoplanet science, illustrating how each new star system discovered can rewrite what we think is possible. This is the allure of TRAPPIST-1, a realm of 7 rocky siblings, all bathed in the soft, ruddy glow of a star that burns only as bright as it absolutely has to, proving beyond doubt that nature's creativity in forming planets is boundless and that our investigations have only just begun.